Picture this: an engine so massive that a grown adult can stand comfortably inside one of its cylinders. A machine so powerful it generates 109,000 horsepower, enough to power a small town. And here's the mind-blowing part. This single engine weighs over 2,300 tons, roughly equivalent to 400 fully grown elephants. Welcome to the world of marine diesel engines, the beating hearts of the world's largest cargo ships. Today we're taking you inside the factories where these mechanical giants are born. You'll witness precision engineering on an unprecedented scale, where tolerances are measured in micrometers despite components weighing several tons. And stick around until the end, because we'll reveal the most critical moment in the entire assembly process. A test that determines whether months of work will succeed or result in catastrophic failure. Before we dive into the construction process, let's understand exactly what we're dealing with here. The largest marine diesel engines, like the Wärtsilä Sulzer RTA 96C, stand as tall as a 4-story building. These engines can be up to 90 feet long and weigh more than the Eiffel Tower's metal structure. But size isn't everything. It's the engineering precision that truly astounds. Despite their enormous dimensions, these engines operate with tolerances tighter than a human hair's width. A single cylinder in these engines displaces more volume than most car engines combined. We're talking about pistons that are nearly 40 inches in diameter, moving up and down with incredible force. These behemoths don't just power ships. They are the reason global trade exists as we know it. 90% of the world's goods travel by sea, and these engines make that possible. But how exactly does one build such a colossal machine? Stay with us because the first step might surprise you. Every massive marine engine begins its life in a specialized foundry, where the engine block, the very foundation of the machine, is cast. This isn't your typical metalworking operation. We're talking about pouring hundreds of tons of molten iron into precision molds. The process starts with creating a massive sand mold, reinforced with special binding agents that can withstand extreme temperatures. Engineers use 3D modeling and decades of experience to design cooling channels within the mold, ensuring the metal solidifies evenly. Any imperfection here could lead to catastrophic structural weaknesses later. When molten iron, heated to over 2,500 degrees Fahrenheit, flows into these molds, it's a carefully choreographed dance. Multiple cranes work in coordination, pouring the metal from different angles to avoid air pockets. The cooling process alone takes several days. Rush it, and you risk creating internal stresses that could crack the block under operational loads. Once cooled, the rough casting emerges, a hulking piece of metal that barely resembles the finished product. This is where precision machining begins. CNC machines, some as large as a house, mill the block's surfaces to exact specifications. The mounting points for cylinders must be perfectly aligned. We're talking about accuracy within 0.01 millimeters across spans of several meters. But here's something most people don't realize. The engine block isn't just one piece. Modern marine engines use a modular approach, and how these sections are joined together involves a technique that will blow your mind. But we'll get to that later. If the engine block is the foundation, the crankshaft is the backbone. This single component can weigh over 300 tons and must be forged from a single piece of steel. Why? Because any joints or welds would become weak points under the tremendous forces this component endures. The forging process is spectacular. A massive steel ingot is heated until it glows orange, then placed under a forge press that can exert 10,000 tons of pressure. With each thunderous strike, the metal is shaped, compressed, and its grain structure aligned for maximum strength. This isn't just about shaping metal, it's about manipulating its molecular structure. After rough forging, the crankshaft undergoes heat treatment, carefully controlled heating and cooling cycles that harden the surface while keeping the core flexible. This gives the crankshaft the perfect combination of wear resistance and toughness. It won't crack under the cyclical stresses of millions of rotations. Machining the crankshaft is where artistry meets science. Each journal, the section where connecting rods attach, must be perfectly round and smooth. We're talking about surface finishes measured in microns. Special grinding machines work for days on a single crankshaft, removing microscopic amounts of material with each pass. The balance is crucial. Even a slight imbalance in a component this massive would create vibrations that could tear the ship apart. Engineers use laser scanning and computer modeling to identify where to remove material, achieving balance so perfect that this 300-ton component spins with less vibration than a ceiling fan. Now we come to where the magic really happens. The cylinders where fuel combustion creates power. Each cylinder liner in a large marine engine is an engineering masterpiece in itself. These massive tubes, cast from special alloy steel, must withstand temperatures exceeding 2,000 degrees Fahrenheit and pressures up to 200 bar. That's 2,900 pounds per square inch. The manufacturing process begins with centrifugal casting. Molten metal is poured into a spinning mold, and centrifugal force pushes it outward, creating a cylinder with a dense, uniform structure. This method eliminates impurities and air pockets that could become failure points. The inner surface receives special treatment. It's honed to a mirror finish, then receives a crosshatch pattern at a precise angle. This pattern, invisible to the naked eye, is crucial. It holds oil, providing lubrication while allowing piston rings to seal properly. Get this angle wrong by even a few degrees, and the engine will consume excessive oil or lose compression. The pistons themselves are equally impressive. Each one can weigh several tons and must survive millions of cycles of extreme heat and pressure. They're typically made from forged steel or special aluminum alloys, with sophisticated cooling channels cast inside. These channels circulate oil to remove heat. Without this cooling, pistons would melt within seconds of operation. Here's something fascinating: the piston rings. These seemingly simple components are actually precision devices made from special cast iron with exact spring tension. Too tight and they create excessive friction, wearing out prematurely. Too loose and combustion gases blow past them, reducing power and contaminating oil. Each ring is hand-fitted and tested. Assembly of a massive marine engine is a months-long process that requires hundreds of skilled workers and specialized equipment. It's not just about bolting parts together. It's orchestrating a complex dance of heavy machinery, precision measurement, and experienced craftsmanship. The process typically starts with positioning the engine block on a massive assembly stand designed specifically for that engine model. Then comes the crankshaft installation, an operation that requires multiple overhead cranes working in perfect coordination. The crankshaft, weighing hundreds of tons, must be lowered into position with millimeter precision. Any impact or misalignment could damage bearing surfaces that took weeks to machine. Main bearings come next. These massive bearing shells, some over a meter in diameter, create the friction-free surface on which the crankshaft rotates. They're made from specialized materials, typically steel backed with a layer of softer metal like bronze or babbitt. This softer layer conforms to microscopic imperfections and embeds any debris particles that might otherwise score the crankshaft. Installing each bearing requires meticulous care. The bearing clearance, the microscopic gap between bearing and crankshaft, must be exact. Too tight and friction generates excessive heat. Too loose and oil pressure can't maintain a protective film. Technicians use precision measuring tools and sometimes even adjust bearing thickness by adding or removing shims measured in hundredths of a millimeter. Next come the connecting rods, massive steel components that link pistons to the crankshaft. Each connecting rod for a large marine engine can weigh several tons. They're attached to the crankshaft with bolts that must be torqued to exact specifications using hydraulic tensioning equipment. We're talking about bolt tensions exceeding 100 tons per bolt. The cylinder liners are lowered into position, sealed with specialized gaskets that must withstand enormous pressures and temperatures. Then the pistons, already fitted with their rings, are carefully inserted from below. This operation requires extreme care. Any damage to the honing pattern in the cylinder liner or the delicate piston rings could compromise engine performance. The cylinder heads come last. Each one is a complex casting containing valves, fuel injectors, and cooling passages. They're precision machined and must seal perfectly against cylinder pressures that could easily blow them off if not properly secured. Mounting bolts are torqued in a specific sequence to ensure even clamping force. With the mechanical heart assembled, attention turns to the engine's vital systems, the networks of pipes, pumps, and electronics that keep everything running. The fuel system is incredibly sophisticated. Fuel injectors for marine diesel engines operate at pressures up to 2,000 bar. That's 29,000 psi. At these pressures, fuel spray can cut through skin like a knife. The fuel lines, pumps, and filters must be assembled with absolute cleanliness. A single grain of sand could block an injector or damage a precision machine pump. The lubrication system circulates hundreds of gallons of oil through the engine. Not just to reduce friction, the oil also cools pistons, removes contaminants, and cushions loads on bearings. The oil pumps are massive, capable of flowing thousands of gallons per minute. Filtration systems remove particles down to a few microns in size. Cooling systems are equally complex. Seawater is pumped through heat exchangers to cool the engine's freshwater cooling system. The fresh water circulates through the engine block, cylinder heads, and oil coolers. Temperature control is critical. Too cold and the engine runs inefficiently. Too hot and components fail. The engine control system is the brain coordinating everything. Modern marine engines use sophisticated computer controls, monitoring hundreds of parameters thousands of times per second. Sensors measure temperatures, pressures, speeds, and vibrations. The control system adjusts fuel injection timing, turbocharger settings, and cooling flow to optimize performance and protect the engine. After months of assembly, the moment every engineer both anticipates and dreads arrives, the first startup test. This is where we discover if all those weeks of precision work have paid off, or if a critical error will reveal itself catastrophically. The preparation alone takes days. Every system is checked, double-checked, and triple-checked. Oil levels, cooling water flow, fuel quality, electrical connections, nothing is left to chance. Experienced test engineers review every parameter. They've seen what happens when things go wrong, and nobody wants to witness a multi-million-dollar engine destroy itself. The engine is started on compressed air first. No combustion, just rotating the crankshaft to verify everything moves freely. Technicians listen carefully for any unusual sounds, grinding, knocking, or rubbing that would indicate a problem. They monitor oil pressure, looking for the steady readings that confirm all bearings are properly lubricated. Then comes the nerve-wracking transition to diesel operation. Fuel is introduced gradually and the engine begins firing. The first few revolutions are critical. This is when any assembly error will most likely manifest. If a bearing clearance is wrong, or a piston ring isn't seated properly, or a bolt wasn't torqued correctly, now is when it fails. As the engine warms up and reaches idle speed, engineers monitor hundreds of parameters. Exhaust temperatures from each cylinder must be nearly identical. Differences indicate problems with fuel injection or compression. Vibration sensors detect any imbalance or mechanical issues. Oil samples are analyzed for metal particles that would indicate wear. The real test comes under load. The engine is connected to a dynamometer, essentially a massive brake that simulates ship propeller load. Power is increased gradually, bringing the engine to its full rated output. Now it's generating tens of thousands of horsepower, with each cylinder producing more power than several car engines combined. This is the moment of truth. If the engine can run at full power for several hours without issues, maintaining proper temperatures and pressures, exhibiting no unusual vibrations or sounds, and showing no signs of leaks, then it passes. The relief in the testing facility is palpable. Months of work have succeeded. What you've just witnessed is one of humanity's most impressive manufacturing achievements. the construction of engines that power global commerce. These massive diesel engines represent the pinnacle of mechanical engineering, combining brute strength with microscopic precision. From molten iron poured in massive foundries to final testing under full load, building a marine diesel engine is a testament to human ingenuity and craftsmanship. Hundreds of workers, each experts in their field, collaborate to create machines that will run continuously for years, powering ships that carry the goods our modern world depends on. The next time you see a container ship on the horizon or receive a package shipped from across the ocean, remember the engineering marvel hidden deep in that ship's hull. A massive diesel engine, meticulously built by hand, powering global trade one revolution at a time. If you enjoyed this deep dive into marine engineering, don't forget to like this video and subscribe for more fascinating looks at how the world's most impressive machines are built. What should we explore next? Let us know in the comments below.